Okay, welcome to Coy Rawson Schools. We're sitting here in Ohio, USA, right along Route I-75. It's within walking distance of here. And we're at about the 41st parallel. And we're here today to talk about that here in North America, at least, you and I and everything tilts slightly towards the equator. I first realized this, I think it was the 2019-2020 school year on a snow day, and I was in here working around, not particularly busy at all. And all of a sudden it dawned on me, we tilt towards the equator slightly. So I figured it out. Everything on the Earth's surface tilts towards the equator. Now, let's set the stage here. Vertical things tilt towards the equator just slightly. This is a problem involving resolution of vectors. So if you're working on vectors, this is a good thing to kind of pay attention to. The vectors involved include the acceleration of gravity and centripetal acceleration. We are going to use, usually I think it's, you use what's called the inertial, you don't use the inertial frame of reference, or you do, forget. We don't use, for example, centrifugal. Well, today we're going to, because it's easier to follow the explanation. You can reverse engineer it to do a centripetal acceleration on these if it so pleases you. It's just a little easier to do centrifugal. We will use the Earth's latitude of 41 degrees north, which is what it is right here in Putnam County. I think road M is 41 degrees. The 41st parallel is just a few miles north of here, between here and Benton Ridge, somewhere just south of Benton Ridge. We'll incorrectly assume the Earth is perfectly spherical. We'll assume that surface gravity is an absolutely uniform 9.8 meters per second squared, just to reduce variables. There's geographic poles in the equator. The tilt becomes 0. And the maximum tilt is somewhere between, I have not attempted to work out what degree that should be a maximum. Okay, we're going to use a rotating frame of reference instead of the conventional inertial frame. So you have this resolution of vectors problem that occurs here, and you don't have that problem at the equator, and you don't have that problem at the North Pole. In the North Pole, you're just doing this once a day, or the South Pole. And so you don't have another vector with that you have to resolve, just straight down. At the equator, if you did centrifugal force, you'd have a vector, or centrifugal acceleration, you'd have one that way, and gravity would be this way, they'd be lined up, and they would just add positive, negative. You have a vector problem everywhere else in between. Okay, so let's use centrifugal. As the Earth spins in a circle, centripetal acceleration is v squared over r, and that velocity is once around that circle, once a day, so it's 2 pi r over t. And if you square that, the centripetal acceleration is 4 pi squared r over t squared, where this is the day length in seconds, that's the radius of the Earth, and the radius of the Earth is about 6,380 kilometers, so 6.38 times 10 to the 6 meters, and 3,600 seconds in a day times 24 hours, and then square that. That centripetal acceleration works out to be 0.03374 meters per second squared-ish at the equator. But it's 0 there, and it's less everywhere in between. Okay, so if we work out at 41 degrees, this length of side, where it's 0.03374 meters per second squared at the equator, it's less and less and less and less and less. So that vector, this side would get less everywhere. At 41 degrees, that's 0.03374 meters per second squared times cosine of 41 gives us 0.02546 meters per second squared. And if I take that vector and resolve it, where this is up and down locally here, it has a component this way and a component that way. So if we say our acceleration where we're at here at 41 degrees is straight down, spherical Earth, sorry flat earthers, you have to go somewhere else. 9.81000 meters per second squared down. This is 0.02546 at this angle with a component up that's smaller and a component towards the equator that's smaller. So this blue vector is downward, resolving this vector, this one, and this one gives us an angle of tilt. So that guy has components this way of 0.01921 and a component this way of 0.01670. This would, if you're doing centrifugal, would subtract off the 9.81, or if you wish this is positive, 9.81 is negative. And then that one would take it a different way. So these are our x components and y components of the acceleration of gravity. And then you get 9.79233 and 0.01921. Your new angle between those two is 0.112 degrees. So we tilt slightly towards the equator at 0.112 degrees. Now, you would find it very taxing, difficult to measure this because the levels are doing the same thing. The plumb bobs are doing the same. So it would take quite a meticulous setup in a very big room to measure this and see that it's off a little bit. Maybe NASA engineers would do this, but it'd take time and a budget. It could be done. I don't know about the high school level. You'd have to be very controlled with your temperature and stuff, so nothing shrinking, expanding, because this isn't very much. It works out, if I remember right, to, let's see, for up at 2 meters high, it works out to less than 4 millimeters of tilt towards the equator. So not very much at all, but it's there. So the amount is very small. The surface of the Earth is not tangent to a perfect sphere because the Earth isn't spherical because it's spinning. It's actually kind of wider in the middle and flatter on the end, or at the poles. And so all the plumb bobs and the levels and the observers and the houses built, everything's out of whack a little bit. It would be hard to detect this. So there you go. Interesting.